James Webb may have just detected something in the atmosphere of a distant planet that, on Earth, is produced almost entirely by life. Not a strange radio signal, not a blurry image, not a theory based only on the planet's distance from its star, a chemical signature. A molecule hidden inside the light of a world 124 light years away. And for a brief moment, scientists thought they might be looking at the first real evidence of life beyond Earth. But then something happened. Other scientists began examining the data, and instead of trying to prove the discovery, they tried to destroy it. Because the signal that looked like the strongest evidence of alien life ever detected might also be one of the most convincing false alarms in the history of astronomy, and yet, even after the life claim began to collapse, the planet itself became more fascinating. Because beneath its atmosphere, there may be an ocean covering an entire world, a world larger than Earth, a world with methane, carbon dioxide, a potentially water rich interior, Olushit's Achaean India, and a chemical mystery that scientists still cannot completely explain. So, what exactly did James Webb detect? Did humanity really find the strongest sign of life beyond Earth, or did the universe once again give us something that looked like biology but was actually just chemistry? The answer begins with a planet called K218b, and the strangest thing about this world is that we may be able to study its atmosphere without ever going there. The planet that should not have been this important. The story of K218b began in 2015. At first, it was just another distant planet discovered by NASA's Kepler Space Telescope, and that sounds ordinary. Because by that point, astronomers had already discovered thousands of planets beyond our solar system. But K218b had something that made it different. Actually, it had three things. The first was its size. K218b is much larger than Earth. It is roughly 2.5 times wider than our planet and several times more massive. That places it in a category called a sub-Neptune, and this is already unusual. Our solar system contains small rocky worlds, Mercury, Venus, Earth, Mars, and then we have massive gas and ice giants, Jupiter, Saturn, Uranus, Neptune. But we do not have a planet exactly like K218b, a world between Earth and Neptune, and yet these planets appear to be incredibly common throughout the galaxy. The universe seems to make them everywhere. Our own solar system simply does not have one. But the size of K218b was not the reason scientists became interested in the possibility of life. The second reason was its star. K218b orbits a red dwarf, a star much smaller and cooler than our Sun, and because the star is so dim, the planet can orbit much closer to it and still receive an amount of energy that could potentially allow liquid water. This is what scientists call the habitable zone, the region around a star where temperatures could, under the right conditions, allow liquid water to exist. The Goldilocks zone, not too hot, not too cold, just right. But being in the habitable zone does not mean a planet is automatically habitable, and it definitely does not mean there is life. Venus is almost the same size as Earth, but its surface is hot enough to destroy spacecraft. Mars once had rivers and lakes, but today its surface is cold and hostile. So the distance from a star is only the beginning of the story. The real question is, what is the planet actually made of? And this is where K218b became truly interesting. Because from our perspective, the planet passes directly in front of its star, it transits, and that perfect alignment allows astronomers to do something extraordinary. They can study the planet's atmosphere. How can we read the air of a planet 124 light years away? Imagine a star. And imagine a planet passing directly in front of it. Most of the starlight travels straight toward Earth, but a tiny fraction of that light passes through the planet's atmosphere first. And that is where the information is hidden. Every molecule absorbs specific wavelengths of light. Water vapor absorbs certain wavelengths, methane absorbs others. Carbon dioxide leaves its own chemical fingerprint. So when astronomers split the light apart, they can look for the missing wavelengths, and those missing pieces can reveal the chemicals present in the planet's atmosphere. Think about what that actually means. The light we receive from K218b began its journey more than a century ago. It left that distant star system before many people alive today were even born. It crossed 124 light years of empty space, and eventually that ancient light entered a telescope built by human beings. Inside it was information about the air of another world, a world we cannot visit, a world we cannot land on, a world whose atmosphere we can nevertheless begin to read. That is one of the strangest abilities humanity has ever developed. We can study the chemistry of a planet without ever touching it. In 2019, the Hubble Space Telescope made an important attempt. Researchers reported a possible detection of water vapor in the atmosphere of K218b. If true, it would be significant. It would be the first reported detection of water vapor on a planet located in the habitable zone. But there was a problem. The signal was not clear enough. Some researchers believed the data could indicate water vapor. Others argued that methane might produce a similar pattern. The planet was hiding behind uncertainty, and to solve the mystery, astronomers needed a more powerful instrument. Then, in December 2021, that instrument left Earth, the James Webb Space Telescope. The telescope that could finally answer the question James Webb was built to see things previous telescopes could not see with the same precision. Its enormous gold-coated mirror was designed to collect extremely faint infrared light. Its instruments were built to study the chemical fingerprints of distant worlds, and after reaching its position in space, it began doing something that had never been possible at this scale: reading alien atmospheres. In 2023, astronomers pointed James Webb toward K218b, and the results immediately made the planet more interesting. Methane appeared to be present, carbon dioxide appeared to be present, and those two chemicals together began creating a picture of a world very different from Earth. But then scientists noticed something else, or rather, they noticed something that was missing: ammonia, and that absence mattered. If K218b were simply a giant ball of hydrogen-rich gas, ammonia might be expected in its upper atmosphere, but they appear to be very little. So scientists began asking a strange question: what if something below the atmosphere was absorbing it? What if the planet was not simply a gas-rich world? What if it contained an enormous ocean? Not an ocean like the Pacific, not an ocean with islands and continents, a planet-wide ocean. A world where the water may cover almost everything. Scientists have proposed a category of worlds known as Hycean planets, planets with hydrogen-rich atmospheres and potentially vast oceans, and K218b may be one of the best candidates for this kind of world. Try to imagine standing there. Actually, you could not stand there. There may be nowhere to stand, no continents, no beaches, no familiar horizon, just water stretching in every direction. Above you, a red dwarf star, a strange orange light, and beneath you, an ocean descending to depths far beyond anything on Earth. The pressure would increase as you went deeper, the chemistry would become more extreme. The water could exist under conditions that humans have never experienced, and somewhere in that enormous environment, life could theoretically exist in ways we have never imagined. But this was only the beginning, because hidden inside the James Webb data there was another signal, and this one changed the entire story. The molecule that made the world ask, are we alone? The molecule was called dimethyl sulfide. On Earth, dimethyl sulfide is strongly associated with biological activity. Marine organisms can produce it. Microscopic life in our oceans can release it into the atmosphere. And that makes the molecule extremely interesting, because if scientists detected it on another planet, they would have to ask an obvious question: where did it come from? In the 2023 observations of K218b, researchers noticed a faint signal that could potentially be associated with dimethyl sulfide. The signal was not perfect, it was not definitive, but it was there. And suddenly, the planet that had been an interesting exoplanet became something much bigger: a world in the habitable zone, a possible ocean world, methane in the atmosphere, carbon dioxide in the atmosphere, and now a molecule associated with life on Earth. The headlines exploded. Have we found life beyond Earth? But this is where the story becomes much more complicated. Because a possible biosignature is not the same thing as proof of life. The signal was around 3 sigma. That sounds extremely impressive. But in science, especially when the claim is extraordinary, it is not enough. The highest standard for a major discovery is much more demanding: 5 sigma. A signal must survive extremely aggressive statistical scrutiny, and the K218b result had not reached that level. The scientists knew this. They did not claim they had confirmed alien life. They said the result was intriguing. They said more observations were needed. And then the rest of the scientific community began doing what it was supposed to do. They attacked the signal. Scientists tried to destroy the discovery. This is the part that most headlines did not explain. When a possible discovery appears, other scientists do not simply celebrate. They ask, can the result be reproduced? Could the signal be caused by noise? Could another molecule create the same pattern? Could the data be interpreted differently? And when researchers began reanalyzing the K218b observations, the possible biosignatures started to look less certain. Some teams used different statistical methods, and in some of those analyses, the dimethyl sulfide signal became much weaker. In many of the analysis runs, it appeared to disappear almost completely. Then another problem appeared. The chemical fingerprint may not have been unique. Other molecules could potentially produce similar signals. At the resolution available, the telescope may not always be able to perfectly distinguish one chemical from another. A signal that looks like dimethyl sulfide would potentially be produced by another molecule. And then came an even more important realization. Dimethyl sulfide may not be exclusive to life. On Earth, biology is a major source, but Earth is only one planet, one environment, one example of chemistry. The universe may be capable of producing the same molecules through processes that do not involve life at all. A molecule associated with life is not automatically a molecule created by life, and that is one of the biggest dangers in the search for aliens. Scientists are not simply searching for chemicals, they are searching for chemicals that cannot be explained by anything except biology. And that is an incredibly high standard because the universe is very good at creating strange chemistry. Sometimes a signal can look like life and still be completely lifeless. The life signal may have weakened, but here is the part that makes K218 so interesting. The possible life signal became controversial, but the planet itself did not suddenly become uninteresting. In fact, some of the most important evidence remained: methane, carbon dioxide, a possible water rich environment, and the possibility that K218 may contain a massive amount of water, possibly a significant fraction of the planet's total mass. Now compare that with Earth. Earth looks like a water world from space, but by mass, the water on our planet is only a tiny fraction of the total. The oceans are enormous to us, but on the scale of an entire planet, they are relatively thin. K218 could be very different. Its water may not be a thin layer covering a rocky world. The water could represent a much larger part of the planet itself, a world where the ocean is not merely sitting on the surface but is a defining part of the planet's entire structure, and that changes the question. We are no longer simply asking, is this another Earth? It may not be. The better question is, can life exist in a world that is nothing like Earth? Because if the answer is yes, the number of potentially habitable worlds in the galaxy could become enormous. Sub-Neptunes appear to be extremely common, and if even a fraction of them contain liquid water, the universe may contain billions of environments where life could potentially emerge, not Earth-like planets, not blue planets with continents, something completely different, ocean worlds, hydrogen worlds. Worlds where life, if it exists, may have evolved under conditions that would be completely alien to us. But is K218b actually habitable? This is where we need to be careful, because the word habitable can create the wrong image. K218b is not a place where humans could simply land. There is no evidence that humans could breathe its atmosphere. There is no evidence that the surface would be comfortable. There may not even be a solid surface in the way we imagine one. And the same models that allow the possibility of a warm ocean can also allow much darker possibilities. If the planet's atmosphere traps too much heat, the water may become extremely hot. It could exist in a supercritical state, not a calm blue ocean, not an environment where life as we know it could easily survive. Some models suggest the planet may have an environment that is far more extreme than the original headlines suggested. And then there is the star. K218 is a red dwarf. These stars can be active, they can produce powerful flares, they can bombard nearby planets with intense radiation. K218b orbits much closer to its star than Earth orbits the Sun, so even if liquid water exists, the environment could still be extremely hostile. This is why scientists cannot simply look at one chemical and declare life. They need the entire planetary environment, the atmosphere, the temperature, the chemistry, the star, the possible ocean, the geological processes. Everything has to be considered because life is not just a molecule, life is an explanation, and the explanation has to survive every alternative. So, what did James Webb actually find? At this point, we can separate the facts from the mystery. K218b is real. It is much larger than Earth. It orbits a red dwarf star. Its location may allow conditions where liquid water could exist. Methane has been detected in its atmosphere. Carbon dioxide has been detected. The planet may be extremely water rich. It may contain a vast ocean beneath a hydrogen rich atmosphere. These are the parts of the story that make K218b one of the most important exoplanets scientists can study. But the most exciting part, the possible biosignature, remains unresolved. The dimethyl sulfide signal is interesting. It is scientifically important, but it is not proof of life. Not yet. And that not yet is what makes the future so fascinating, because more observations could change everything. Every time K218b passes in front of its star, James Webb has another opportunity to study its atmosphere, another transit, another sample of light, another chance to separate the chemical signals, and with enough observations, scientists may eventually determine whether the possible biosignature is real or whether it was simply noise, a statistical accident, or another chemical pretending to be life. Either result would be historic. If the signal becomes stronger, the case for biology becomes more interesting. If it disappears, we will learn that the universe can produce one more convincing false alarm, and that is still valuable, because the search for life is not about confirming every exciting possibility, it is about eliminating every explanation that is not life, until eventually one remains. The answer may already be on its way. For almost the entire history of humanity, the question, are we alone, was philosophical. People could look at the stars, they could imagine other worlds, they could debate whether life existed elsewhere, but they had no way to test the question. Now we do. We can detect planets orbiting other stars, we can measure their atmospheres, we can search for chemical fingerprints, we can compare different worlds, and K218b may be one of the first planets where the question of life becomes a real scientific measurement, not a dream. Not a philosophical argument, a measurement. Think about the strange position humanity is in right now. The light carrying information about K218b has already traveled 124 light years. It left that distant world more than a century ago. It crossed the darkness between the stars, and eventually it arrived at a telescope built by a species that only recently learned how to leave its own planet. Inside that light, there may be an answer. Maybe not the answer we want. Maybe K218b is completely lifeless. Maybe the possible biosignature will eventually disappear. Maybe the ocean is too hot. Maybe the atmosphere is too hostile. Maybe the chemistry has nothing to do with biology, but there is another possibility. What if the signal survives? What if future observations confirm it? What if independent teams analyze the data and the same chemical pattern continues to appear? What if every non biological explanation fails? Then the story changes completely, because humanity would no longer be asking whether life could exist beyond Earth. We would have evidence that it does. A second living world, 124 light years away, possibly beneath an alien sky, possibly inside an ocean that covers an entire planet. And that discovery would change our understanding of life forever. Not because we found intelligent aliens, not because another civilization contacted us, but because we would finally know something even more fundamental. Life is not unique to Earth. That is the possibility hiding inside K218b. And that is why this planet matters even if the current biosignature claim eventually fails. Because every observation teaches us how to search. Every false signal teaches us what life is not. Every confirmed chemical teaches us how to read an alien atmosphere. And eventually, somewhere, the evidence may become impossible to ignore. The question is not whether the universe is capable of creating life. We already know that it can. The question is whether Earth is the only place where it happened. And for the first time in human history, we have machines powerful enough to begin looking for the answer. So, did James Webb just detect the strongest sign of life beyond Earth? The honest answer is we do not know yet. But James Webb may have found something almost as important, a world where the search can actually happen, a world with an atmosphere we can study, a world with carbon bearing molecules, a world that may contain enormous amounts of water, and a world where a possible chemical signature of life has already appeared in the data. The signal may disappear, or it may become stronger. And if that happens, the next few observations of K218b could become some of the most important observations in the history of science, because the answer may already be here, not traveling toward us from some distant future, not waiting for a spacecraft to arrive. The light has already arrived, it is already inside the data, and somewhere within that ancient light, there may be a message from a world we have never seen. The only question is, what will we discover when we finally learn how to read it? If you want to follow the next chapter of the search for life beyond Earth, subscribe, because the next major observation of K218b could either destroy the most exciting alien life claim in modern astronomy or bring humanity closer than ever before to answering the oldest question of all: are we alone